Hi everyone. Today, let's talk about session 2.3, Newton's method. So like the regular Fossey and secant method, Newton's method used a strict line approximation to the function f of x. But instead of the secant lines of 2 points, here we consider the tangent lines at 1 point. The approximation to the zero is the value of the x, where the tangent line crosses the x-axis. Okay, so let me draw a picture here. Okay, so instead of f over an interval, we would just have initial points x0. Okay, so let's say our f like this. Let's say this is x0. Okay, and then we have this is the y0. Okay, then we can consider the tangent line at x0. So tangent line, let me draw it here. So that is the line tangent to this curve. Okay, and you can see it passed through the x-axis at x1. Let's say x1. So x1 is our estimated value. Okay, so how this work? Given the initial estimate of the 0 x0, the value of the function at x0 is y0, and the value of the derivative, so y0 prime is the derivative f prime of evaluates at x0. Okay, then the new approximate 0 is the value of x, where the tangent line cross the through the initial point cross the x-axis. Okay, so this is tangent line through the initial point x0 y0, and let's find out what it is. Okay, remember we have Poinsot form. Okay, y minus, so here, what is the point? The point is x0, y0. Well, the slope is y0 prime. So that's why Poinsot form is y minus y0 equals y0 prime, x minus x0. And we want to find the x-intercept. So we set y equals 0, and we want to solve for x. Then we have minus y0 equals y0 prime, x minus x0. Then x minus x0 equals minus y0 over y0 prime. And then, so x is both sides at x0. x0 minus y0 over y0 prime. So far, so good, everybody? Okay, so this is the new approximated 0. Okay, and at the k stage, well, we will have x sub k plus 1 equals x sub k minus y sub k over y sub k prime. So far, so good, everybody? Okay, so unlike the previous methods, so let's count how many methods we learned so far. We learned the bisection method, regular Fossey method, and secant method. Right? All of them we were given the interval, and f has a 0 inside the interval. But the Newton's method, we only given initial points. Okay, so initial points. So it's one value, it's not like two values. Okay, so let's see. Example 1. Consider the function y equals 4x squared minus 3 with the interval 0, 1 if we pick x0 to be 0.5. And let's see what we do. Okay, in order to calculate the estimated 0 for the next step, we need to compute the derivative. So here, y prime. So because in this process we need to take the derivative, I hope that you're familiar with all the derivative formulas and in Cal 1. Okay, if you forget all of them, please go to my course website. Then you can see my Cal 1 worksheets. Okay, and then there you will find the derivative formulas. So please review those. Okay, so let me see. I can probably show you here. So go to my website. Let's see here. Okay, go to my calculus 1. And then the first week you see this calculus formula sheets. And then we have all the common derivatives and integrals. Okay, so here are the common derivatives and integrals. All right. Okay, let's continue. Okay, so derivative of constant multiples stay there, so 4 stay here. Derivative of x squared is 2x. So that is 8x. Okay? Sometimes if we have more complicated functions, you might expect to use product rule, quotient rule, and chain rule. Okay, so after that, we're ready. So x0 equals 0.5. Okay, and let's figure out a formula. Okay, so here xk plus 1 equals xk minus yk over yk prime. And what is it? Well, yk is 4xk squared minus 3, right? Our function, just plug in x equals xk. Yk prime is then the derivative. We plug in x equals xk. So we have 8xk. So far, so good, everybody? So this is the iterative formula. Alright. Now, what is x1? Well, x1 is x0 minus 4 x0 squared minus 3 over 8 x0. So how do you type this in your calculator? Okay, so I'm going to teach you how to type it in your calculator here. Let me use a different color. How about purple? Okay, so how to type in the calculator. Okay, so first x0 is 0.5, right? So you do 0.5 and then you click enter. I'm gonna show you later, okay, after I write it down. So then you will get the 0.5 in the line. Next step, look at our iterative formula. So this iterative formula tell you we should put answer minus parentheses 4 answer square minus 3 parentheses divided by parentheses 8 answer. Okay, you do this and then you enter. Then you will get x1. Okay, then you go up to the previous line. Okay, go to that equation and click enter again. So here then you will get x2. So each step you just go up to the previous line and click enter. Okay, then so we complete this process. So each step you don't need to retype the formula again. Just go up one line and click enter. Then you will get all the x's. Okay, so I'm gonna show you here. So where is my calculator? I'm my calculator. Okay, here is my calculator. So I let me clear all. Okay, so I do 0.5 enter. Then I have 0.5 in my line, right? And then let me move up a little bit. And then I do answer. You see this answer? Answer minus. So don't click 0.5. Make use of the answer key. Okay, then you do parentheses 4 answer square minus 3, close it, divided by 8 answer. Okay, so in your calculator you have to put the parentheses. Okay, otherwise they will think you divided by 8 and multiply by the answer. Okay, and then that's it. Click enter. Ooh, see, x1 is 1. So x1 equals 1. Let me use my orange color. For x2, just go up. Okay, if you're holding your calculator. So everybody, please, in class when I type something in my calculator, please you do the same thing to do your calculator, because sometimes you really need to type it by yourself, and then you understand the difficulties and the possible mistakes that we may make. Okay, don't ask me how to use your calculator in the exam, because I won't teach you how in the exam. So ask me now, okay? Not in the exam. Before the exam, I can tell you. So please figure out the questions and then ask me the questions. Let me help you. Okay, so with this online calculator, I just copy and paste. See? This is my x2. So x2 is 0.875. Okay, so see, we don't need to make a table. We don't need to type in the function again. Each step we just copy and paste. See, I just paste again. So I get let me see, 0.866071286. Okay, 0.8667 071484286, right? Let's see. Yes. Okay, so go up the line and enter again. We get another one. So x4 is 0.866025405. Okay, so we copy down 0.866025405, right? Okay, continue. Point 866025403.8. You will see the number are getting very close to each other, right? Oh, 4038, sorry. 4038. And one more. Do you see we get the same answer? Yes. So x6, we get the same answer. This is the place we can stop. Okay? Yeah, we just keep going until we get the same answer. Okay? I remember sometimes it looks like you don't need to go up to the previous line. You just click enter. Then you so it really depends on your calculator. So please investigate your calculator. Okay, so if you get an answer and then you click enter, do you get these numbers? Okay, yes, awesome. And if we use MATLAB or Octave to compute, this is what we get. You see, the x values is 0.8660, so that matches with our answer. And this is the function f, right? And you can see the 0 is like 0.86 somewhere. Okay, so it matched with our results. Okay, so how to use MATLAB to compute? All right, so let's look at this problem. The format of the code is brackets x comma y brackets equals capital N newtons, and then we have the function. The function PR is the derivative. Okay, this is the derivative. So we need to input the function and we need to input the derivative. So MATLAB won't calculate the derivative for us. Okay, and this x1 is the same as my x0. Okay, but just in the code I call it x1, and we still have the tolerance and the k mass. Okay, so here this is our y, right? And then what is y prime? Well, this we need to figure out by ourselves. So that is 3x squared minus 2 times 3, 6x. So this is the derivative. Okay, I really want to calculate this problem with you by hand. I want you to see more examples. Why don't we do it by hand as well? So xk, x0 is 0.5, xk plus 1. We have to figure out the iterative formula. So that is yk. Yk is xk cubed minus 3xk squared plus 4 over 3 over yk prime. So 3 times xk squared minus 6 times xk. Okay, so keep that in mind. So where is our calculator? Here. So clear all, and we type 0.5. That is our x0, right? And then we type in answer minus parentheses answer cube. Then go back down, minus 3 answer square and plus 4 over 3 close parentheses. Oops, you see, this is not so good. So yes, that close parentheses. Then divided by 3 answer square minus 6 times answer. Okay, so enter. So 0.8148148148. 0.8148148148. And then let's continue, copy and paste to see the x2. Okay, so let's see here. Copy and did I copy everything? Okay, copy and paste. Okay, so we get 0.77427. So 77427 and then what? 04826. 04826. Okay, how about x3? So we just keep going until we okay, so this guy and 773926344. 773926344. 39263144. Do I remember it right? Yep. Okay. So continue. 3926. See, you see the it's conversion. The number is getting closer to each other. The 26 before is the same, and then the last digit 2862. Okay. 2862. All right. One more. Oh, do you see we have the same answer? Oh, it converts in the 5th steps. So, same. And then we can stop. So, the estimate is 0. This is our estimated 0. Okay? And okay, now it's time to use MATLAB or Octave. Okay, so let's see. Okay, so here we do x comma y equals Newton in my and then this is x cubed minus 3 times x plus 4 over 3. And you can see that Newton's methods is very nice because we don't need to draw the table. We just figure out the iterative formula and we just do enter. But the bad thing is you gotta compute the derivative by yourself first. Okay? And also, because it does not bracket the 0, we don't guarantee convergence. Okay? So 6 times x. Oops. Okay, and x0 is 0.5. And then the tolerance, let's do 0.000. Let's give me all ones. Okay, and let's do 10 iteration. Syntax error. Let's see. Oh, okay. I missed a quotation mark here. Yeah, sometimes we have to be very careful because a little mistake then we'll get error. Okay, everybody. So let's see. Okay. Oh, you know what? I make a mistake again. This 3x, it should be 3x squared. That's why our numbers doesn't match. Yeah, so to see, we have to be very careful. Square. Okay, now it works. See? 0.77393. Yeah, if we round up, we get 3. So far, so good. And you can see we use our calculator and calculate it by hand. We can get accurate answer in very just in 5 steps. But it really depends on the problem. Sometimes some problems you might get the answer. You might get a very good estimations in 5 steps, but sometimes it might take you 100 steps to get a good approximation. Okay. And here is what happened if I type this in MATLAB. Okay. All right. So fact. Newton's method does not guarantee convergence. However, when it does, the order of convergence equals 2, with the rate of convergence lambda is the absolute value of the second derivative evaluated at the true value over 2 times the first derivative evaluated at the true value. Okay, so actually today I'm gonna show you this proof. So last time for the secant method, I just told you the order of convergence is around 1.62, and the rate of convergence I also give to you. But that proof is kind of harder, and this proof is actually easier. So let's go over this proof. Are you ready? Okay, so let's see. Suppose, okay, so here, suppose xk are the approximation to the 0 x asterisk. Okay, now let's consider the Taylor series expansion for f of x near xk. Okay, so consider the Taylor series expansion. That's why I need to review Taylor series with you before we start our course, right? We need it. and for f of x near xk. Okay, so what is that? Well, if you can remember, that is f of x equals the Taylor polynomial evaluated at xk. So f prime at xk, x minus xk plus the second derivative. It really depends on how many terms you want to get. So here I just want to get 2 terms, and then this guy is the remainder. We replace xk by we can call this eta. Eta is between x and xk. Okay. So this guy is the remainder. And for eta between x and xk. So far so good. Now let me plug in x equals x asterisk. Then f of x asterisk is 0 because this is the 0 of the function, right? If we plug in, we get 0 equals f of xk plus f prime xk x asterisk minus xk, and then plus f prime prime eta over 2 x asterisk minus xk squared. So far so good, everybody? Okay. Next, I'm gonna move these terms to the left hand side. Okay, and let me reverse the left hand side and right hand side. Then we'll get f prime xk x asterisk minus xk equals negative f of xk negative f prime prime eta over 2 x asterisk minus x2 xk squared. So far so good, everybody. Now let's divide it by f prime of k. So then on the left we have x minus x asterisk minus xk equals minus f xk over f prime of xk minus f prime prime eta over 2 f prime of xk. And here we have x asterisk minus xk squared. Okay, now I can add xk on both sides. And this is what we get. So far so good, everybody? Okay, now something amazing happened. What is that? Whoa, look at this. This is actually our iterative formula. This is actually xk plus 1 by Newton's method. Right? Xk plus 1 is xk minus yk over yk prime. Okay? So, what does that mean? Okay, it means that if I move this xk plus 1 on the left, okay, so now, oops, okay, I pressed the wrong button. So if Newton's method converge, okay, then we have xk plus 1 converge to x asterisk, right, when k goes to infinity, right? So when I move this to the left hand side, and we will see x asterisk minus xk plus 1 equals negative f prime prime eta over 2 f prime xk times x asterisk minus xk squared. Okay, if we give them an absolute value, then this becomes absolute value of f prime prime eta 2 f prime of xk, and this is x asterisk minus xk squared. Okay, now so if the Newton's method converges, then well, we have xk plus 1 will converge to xk, right? So it means xk will converge to let's see here. Then we will see. Let me write it that way. Okay, do you see this is the 2? This is actually the p, and then this is the rate of convergence, lambda. Okay, and what is lambda? Well, here you can see limit k goes to infinity, x asterisk the true value minus x sub k plus 1, the true value minus x sub k squared is this lambda. Okay, and the lambda is f of eta f prime xk. Well, because they converge, if Newton's method converge, well, the top guy, remember eta is between x and xk. If xk converge to if xk is converged to the true value, then this guy is just f prime prime the true value over 2 f prime of the true value. So far so good, everybody, and this is the rate. This is the rate of convergence. So that is why you get the p, the order of convergence equals 2, and the rate of convergence lambda equals the second derivative evaluated at the true value over 2 times first derivative evaluated at the true value. So far so good. So we get this from the Taylor series. All right. Okay, nice. Questions. Do you need to remember all of this in the exam? No, you just need to remember, well, for Newton's method, even though we don't guarantee convergence, but if it does, the order of convergence is 2. So, and do you remember the regular Fawcett method? The order of convergence is 1, and the secant method, the order of convergence is 1.62. So you can see, if all 3 methods, the regular Fawcett method, secant method, and Newton's method, if all of them converge, then Newton's method will converge faster than the other 2. So far, so good, everybody? Okay. Because we don't guarantee convergence, so we have a convergence theorem for the Newton's method. And here the conditions is very close to the convergence theorem for the secant method. Okay, so first we still need to require f prime and f prime prime are continuous for all x near a neighborhood of the true value. And then the f prime of the true value is not 0, because look at our rate of convergence is in the denominator. You don't want your denominator to be 0, right? Otherwise, we want the lambda to be small. We don't want the lambda to be big. And 3, x0 is chosen sufficiently close to the true value. Then, conclusion, the iterate xk plus 1 equals xk minus f of xk over f prime of xk. I think there is a typo here. Sorry. Okay. Yes. So this guy will converge to the true value. Furthermore, this is our rate of convergence. Okay. So here, I want to give you an example because we have done many examples that it converge, right? We can calculate it and we figure out the estimate is 0. It converge. I want to give you an example when it failed to converge. So let's look at this qubit function. X cubed minus 3x squared plus x plus 3. Okay. Let's say we pick 1 to be the initial point. And if we input this guy in our MATLAB or Octave, okay, then this is what we get. What happened? You see? 1, 2, 2, 1, 1, 2, 2, 1. It just flicked back and forth. And why is that? Look at this picture. Okay, so we are at 1, right? So this is x0 is 1. Then this is our y0, okay? At y0 is at 2. When we draw the secant line, right? When we draw the secant line there, it intersects. It intersects the x-axis at x1. x1 equals to 2. Then we look at, oh, f of x1 is y1 is 1. And then consider the secant line passing through it. And intersect, use it to intersect the x-axis. Oh, you see, I get x0 back. So that's why the process will oscillate between those two values and we don't converge. It is coincident that the tangent line at that point passing through this point, and then the corresponding tangent line at that point pass through the same point here. So, yes. Okay. I don't want to make my graph so messy. So, then you know what I mean, right? I hope so. So, it is coincident that we have those values oscillate. Okay? So, in this case, we don't have convergence. So far, so good, everybody? Okay, so that is the Newton's method. Next, let's talk about when we have repeated roots. Okay, so we know that in order to have it converge, the derivative at the true value cannot be 0. But so what if we have a repeated root? So Newton's method loses its quadratic convergence in the case of a repeated root. However, we can modify the method to preserve the rapid convergence if the order of the repeated roots is known. Okay, so before we get into that, let me recall something, okay? Some definition. An element A is called a root of multiplicity k of f of x if there is a polynomial s of x such that s of a is not 0 and f of x equals x minus a to the power of k s of x. Well, what does that mean? So, for example, if f is a polynomial, then factor completely. Okay, so factor f completely. Let's say f equals 3x minus 1 squared, x plus 5 to the 7, and then 2x minus 9 to the 11. Well, multiplicity of the roots of the root, oh, this what's this root? 1/3. Multiplicity of the root 1/3 equals 2. So 2 is the number of copies of the corresponding factor. Okay? The multiplicity of this root -5 is 7. The multiplicity of the root 9/2 is 11. It's the number of copies of the corresponding factor in the factorization of f. So far, so good, everybody? That's why you see, oh, we have this factor, and then this guy, s of a is not 0. Okay? In general, if f is not a polynomial, okay, for a differentiable function, k is the multiplicity of a root a if f of a is 0, f prime of a is 0, and the k minus 1 derivative eval at a is 0, but the kth derivative eval at a is not 0. Okay, why is that? Think about the easiest example. X squared. Well, we know x squared, we know the multiplicity is 2, right? So, and the 0 is 0. So f of 0 is 0. And what is f prime? Well, f prime is 2x. So you can see when you plug in 0, f prime of 0 is also 0. But what's f prime prime? F prime prime is 2. Oh, see, f prime prime. The second derivative is not 0. So the multiplicity is 2. So the multiplicity is k when the kth derivative is not 0, but the previous k minus 1 derivative and the lower derivatives, they're all 0. So far, so good, everybody. So I really hope those examples can help you to understand the definition. Okay, if you think you need more examples, please think about more examples. And if you have questions, don't forget to ask me. I'm happy to help you. Okay, so let me know your questions. So example 4, show that x equal to 0 is the root of f of x equals sine x squared. What is its multiplicity? Okay, so now let's see. F of x is sine x squared. And how do we test whether it is a root? We plug in 0. And then we have sine of 0 is 0. Yes, it is a root. Okay? And furthermore, we have f prime of x. Okay, what's the derivative? Well, chain root, the root of sine is cosine x squared, and then chain root, the root of x squared is 2x, right? And when we plug in 0, oh, because the x is here, so when we're plugging 0 is 0. Okay, and let's do one more derivative. Well, then this is a product. We need product rule. Derivative of the first guy. Let's do it slowly. Derivative of first guy times second guy plus the first guy times the derivative of second guy. Well, the root of cosine is minus sine x squared, and because of chain rule, we have a derivative of x squared is 2x, and there is another copy of 2x here, right? And here we have cosine x squared, derivative of 2x is 2. Now we plug in 0. What happened? We plug in 0. This guy has the x, so it's gone. But this guy, cosine 0 is 1. Oh, see? We get it 2, so it's not 0 because the second derivative is the first, it's the first derivative we see is non-zero. Okay, so the multiplicity is 2. Let me put it down there. Okay, so you can see. So the multiplicity equals 2 in this problem. So far, so good, everybody? Okay, if it's polynomial, you can use this method, keep taking the derivative, or you can just factor it completely, okay? If the function is not a polynomial, then you have to keep taking the derivative until you find the first non-zero derivative, okay? And whatever that order of the derivative it is, then the multiplicity is that number. So far, so good. Oh, I don't know whether some of you might get confused. I mean that the 2 is from the second derivative, not from this number. It is a coincidence that this number is 2. So even though this number is 3, the multiplicity is still 2. It's the order of the derivative, okay, not the value of the derivative. So far, so good, everybody? All right. um let's continue in video part B. All right, so see you soon. Bye.